Okay, so we were talking about q-binomial coefficients. So I'll remind you that the q-binomial coefficient, and choose k sub q, is n factorial over k factorial n minus k factorial. Except that these are all q factorials, and so then n factorial is the product of the q-analogues of the numbers from 1 up to n. And the q-analog of n is the polynomial 1 plus q squared up to q to the n minus 1. Okay? And so I wanted to start today by proving this theorem that I stated last time, which is the following. Let fq be a finite field of q elements. And so from your abstract algebra class, if you've taken it, you know that q is p to the something, some prime to the alpha. And again, if you are not too familiar or you don't remember the details, for this theorem, you could just think that q is a prime, and then this is just z mod that prime. Okay. Then the number of k-dimensional subspaces of the vector space fq to the n is this q-binomial coefficient. So this is what I would like to show now. And again, let me remind you that whenever we talk about q-analogues, these are supposed to kind of mimic phenomena that happen for q equals 1. So when q is equal to 1, this is just n choose k. And now the problem is that it's hard to interpret this statement for q equals 1 because there is no finite field of one element. So this statement doesn't strictly make sense, but this is supposed to be an analog of the statement that a set of n elements has the number of k subsets of a set of n elements is n choose k. This is a q analog of that statement. By the way, let me say something, which is that there is a very interesting paper. I forget who wrote it, but it's about the field of one element. So now you know that there is no field of one element, but somehow what that paper does is that it kind of says, well, if there was a field of one element, then what would happen? And it kind of makes this analogy tighter between subsets and subspaces, between sets and vector spaces. So if that interests you, I think that's an interesting paper to look at. And I'll dig up the reference. I didn't look it up before coming here. But so we're gonna, given that this is an analogous statement to the one about subsets, we're gonna give a kind of a similar proof to the one that we gave for the subsets being n choose k. Okay.
Can you say what this n is again? I'm getting kind of confused with the two n's.
This?
The n.
So here k and n are just integers. N is bigger than k, bigger than or equal to k, and so we're looking at a vector space of dimension n, and then we're looking at the k-dimensional subspaces of it. So we have a big n-dimensional space, and we're looking at the k-dimensional subspaces of it, and we're counting. So for example, this means we're counting the lines in fq to the 7, or we're counting the two planes in fq to the 10, etc. And again, it's very important to remember that this is a finite field, and so this vector space is finite. It only has q to the n elements, which is why it makes sense to count things, right? There's a finite number of lines, etc. Okay. So we're gonna. Okay, so let me make some definitions. So let g of nk be the number we're after. Number of k subspaces. K-dimensional subspaces of q to the n, okay, and let n of nk be the number of linearly independent k tuples b1 up to bk of vectors in FQ2. Okay. And just to remind you, so that when we did this for subsets, we said, okay, n choose k is going to be the number of subsets, and then we said, let's consider the number of ordered subsets. And this was this auxiliary thing that we counted. And so here, this is going to be playing the role of what an ordered k subspace is going to be. So that's why the order is important here. Okay. So I'm going to count this in two ways. So count this twice. Okay, so let's count it once by saying, okay, so to choose my k tuple, I can just choose them one at a time. Okay, so first, let me choose the first vector. Okay, how many possibilities do I have for the first vector? Well, it should be a vector in FQ to the n, right? So it's an n tuple where for each coordinate I have q choices. So that means that there's q to the n vectors here. So I have q to the n choices. Is that the correct answer? It's almost the correct answer, but the problem is that I better not choose 0, because 0 is not linearly independent. So I cannot choose 0. Okay, so other than, so let me say not in 0. Okay, I shouldn't choose the vector 0. Now let's choose the next one. So how many possibilities do I have for V2? Well, again, there's q to the n vectors. Now, how many bad ones are there at this point? Well, I should choose one that is not a multiple of V1, right? How many multiples does V1 have? It has q. V1, 2V1, 3V1, 4V1 until... For each element of the field, there's one multiple of V1. So I need to subtract those q vectors. So choices that are not in the span of V1. Okay, and this is an important thing, which is that V1 is a vector that is not 0. The span of V1 is a one-dimensional subspace, and the key fact that we're using here is that any line in q to the n has exactly q points, and these are the q that I'm discarding. Let's choose the next one now. Choose V3. So again, there's q to the n total, but there's some bad ones, and the bad ones are the ones that are linearly dependent with V1 and V2. I shouldn't choose anything in the span of V1 and V2. Now, how many things are in the span of V1 and V2? Well, V1 and V2 are linearly independent, and so I can just take any combination of them, and those are the span. So there's q possibilities for the coefficient of V1, q for the possibilities for the coefficient of V2. So there's q squared choices here. In general, what I'm going to be using is that if I have an I-dimensional subspace in q to the n, then that's going to have q to the I points. Okay? And that's going to mean that I'm going to get q to the n minus 1, q to the n minus q, q to the n minus q squared, etc. Okay. So finally, when I choose vk, what are the possibilities? Well, it says q to the n minus q to the what? K minus 1, right? So choices not in the span of the previous ones. V1 up to vk minus 1. Okay? And so that means that n of nk is the product of these numbers. Okay? That's n of nk. So that's the first way of counting it. But now we're going to count this in a different way. So we're going to say to choose V1 up to Vk, we're going to follow a different procedure. So the first thing I'm going to do is that I'm going to choose their span. How many choices do I have for the span of V1 up to Vk? Well, V1 up to Vk are linearly independent, and so this span needs to be a k-dimensional subspace. And I can choose any k-dimensional subspace to be my span, so the answer is G of nk choices. Okay? So I choose the span first. And so it's kind of the opposite thing, right? I was in the vector space to the n, and first I just chose the points. First point, second point, etc. Now I'm going to say, okay, I'm in the vector space to the n. Let me choose a k-dimensional flat. Okay? And now let me choose my points inside that flat. Well, when I do that, I'm going to get essentially the same answer, except that instead of being in an n flat, now I'm in a k flat. So for the first guy, I have q to the k choices on that k-dimensional subspace, except not the origin. So there's this many choices for V1. Then I need to choose V2. And again, the point is that if I call this vector space maybe capital V, then this should be in V minus 0. Then V2, I have q to the k minus q choices that are in V, but are not in the span of V1, and so on. Okay. So I got a little crowded here, but I have G of nk choices for this guy, then this, and this, and I continue until I choose Vk, and I'm going to get the same thing again, but with a k instead of an n. And so in total, what I get is that n of n comma k is equal to G of nk times q to the k minus 1 times q to the k minus q up to q to the k minus q to the k minus 1. Okay? If you compare this with the proof for n choose k, it's almost the same proof. And then what we did then, and we're going to do now, is just equate these two things, and that's going to give us a formula for G of nk. G of nk is equal to this over this. So q to the n minus 1, q to the n minus q, q to the n minus q squared, etc., over q to the n minus q to the k minus 1, over q to the k minus 1, q to the k minus q, out to this. Okay. That's my formula for G of nk. And then what remains is to show that this is n choose k q-analogue. Okay. And this is kind of an easy algebra exercise. It should look familiar. It should look similar to you, right? You have n minus 1 up to n minus k, etc. The reason that these q analogues of numbers come up is that what is q to the n minus 1? It's q minus 1 times 1 plus q squared up to q to the n minus 1, which is exactly the q analog of n. So this is q minus 1 times the q analog of n. This is q minus 1 times q times the q analog of n minus 1, and so on. You have to do it, and if you simplify it, you find that it's exactly what we're trying to prove. That is n choose k q analog, and that's what this equals. Okay. So that's the proof, and that shows that these numbers are very natural when you do linear algebra over finite fields. Okay. So that's cool, and I want to push it a little bit further now. Because now I want to count the k-dimensional spaces of f q to the n in a different way. And by doing that, I'm going to give another formula for the q-analog of n choose k. So we already proved this statement, but now I'm going to show that this number is also given by the following thing. So I'm going to just write it down, and then I'll explain exactly what this means. In other words, I'm giving you an interpretation of the coefficient of q to the m as something. What is that something? Let me say p of a k n minus k m is going to be the number of partitions of m with k parts less than or equal to n minus k. So let's talk about what this means. Have I defined partitions in this class yet? I think I haven't. But we've defined things that are very similar. So partitions are very similar to compositions. Remember that the compositions of n are the ways of writing n as a sum of numbers in some order. A sum of positive integers in some order. And a partition is going to be a way of... So a partition of n is a way of adding up numbers to get n where the order does not matter. So a partition of n is some. So we usually use lambda for partition. So it's a weakly decreasing sequence of positive integers such that they add up to n. Okay? So let me write P of n to be the number of partitions of n. So for example, if we do P of 4, P of 5. So we need to write 5 as a sum of positive integers. So there's many ways of doing it. 1 plus 1 plus 1 plus 1 plus 1, or 2 plus 1 plus 1 plus 1, or 2 plus 2 plus 1, or 3 plus 1 plus 1, or 3 plus 2, 4 plus 1, or 5. Did I miss any? I think I didn't. But you see that this is like compositions, except that in compositions, this was considered to be different from 1 plus 3 plus 1. Here they're considered to be the same. Okay. So P of 5 is 7. There's 7 ways of doing it. Okay. And so what I get here is partitions of m where Okay, the parts of a partition are the lambdas. These guys are called parts of lambda. And here the parts should be less than or equal to that bound of n minus k. Okay. And well, since I'm going to prove this, but I'm also going to be talking about a few more things. So let me just make a couple of definitions. Let's see. One good definition to make is that if we look at this partition, or maybe a more interesting one, like use the same one that I used here. So let's say 5, 4, 1. Okay. So this is a partition of 10 with 3 parts, and it's customary to draw a little diagram for this that's very nice and useful.
You mean 10?
What did I say?
Partitions of, well, you said partitions of 10, but there's a 1 there.
So this is a partition of 10 because 5 plus 4 plus 1 is 10. And it has 3 parts, okay? So I'm not yet illustrating that. I'm just showing you a nice way of drawing a partition, just to make a little diagram like this. Where you put 5 little squares, 1, 2, 3, 4, 5, and then you put 4 in the next row. And then 1 in the next row. So that might seem kind of gimmicky, but it turns out to be extremely powerful to do this. And I hope to convince you of that with time. Okay? But for now, this is just some picture. This is called the Ferrers diagram. Ferrers diagram of the partition. Okay? And I should warn you that I could have also, I did 5, then 4, then 1. But I could have done 5 and then 4 above and then 1 above. And sometimes you'll see it drawn like this, and that's called French notation. So usually if somebody learned this from the school of British combinatorialists, then you're going to draw it like this. And if somebody learned it from the school of French combinatorialists, they're going to be drawing this reverse. And I think there's also a different notation, which is the Russian notation, which is maybe flipped over like this. Whenever you go to conferences in this field, people are always making snarky remarks about, oh, you're using French notation or whatever. So I guess this is English notation. Okay. But I mention it so you're not surprised if you see this upside down. Same thing. Okay, so what does that have to do with this? It seems like nothing. But we're going to see that there's a very close connection. So what we're going to do is this. So let me give you a kind of a sketch of a proof. So let's consider some, okay, given a K subspace V of S Q to the n, we can always write, so choose some matrix A such that V is the row span of the matrix. And because this is a K subspace, I can assume that this is a K by n matrix. So this is n, and this is K. So this is going to be a full rank matrix, and the rows are going to span my subspace. For any subspace, you can choose a basis, and so you just choose that basis, and you put it as the rows of A. Okay. Why do I do that? Well, because again, it's a slightly superficial thing, but it's useful to think that k-dimensional subspaces, okay, well, that's the geometry of high dimensions. It's kind of hard to see. And somehow we need to get to partitions. And partitions, what shape do they have? Well, you can think of a partition as a bunch of numbers, or you can think of it as a kind of a table. And it's going to be useful that this is a table. Okay? So what I'm going to do is this. What do we row space, not row space. Row space of this. One thing that we learn in linear algebra is to take a matrix and put it in a standard form, which is called row echelon form. Okay? So I can put A in row reduced echelon form. Is that how you say it?
Yes.
Row reduced echelon form. In other words, V is the row space of A, but then what you do is that you start doing row operations to A. You have these elementary row operations. You remember, you can swap rows, or you can do this elementary, take a multiple of this one and subtract it to the other one. And by doing that, I can get my matrix to have a very nice shape. Let me draw it bigger. Not because it's a different shape, but so that we can see a little bit better. But this is k by n, and this is still k by n. How simple can you make it? Well, what you do is that you go kind of column by column, and you say, okay, in the first column, what's the simplest I can do? Maybe you're unlucky, or lucky depending on your point of view. Maybe here you only have zeros in the first column. If that's the case, then the row reduced echelon form is going to have a 0 here, because no matter what row operations you do, there's going to be a 0 in the first column. Okay? And maybe in the next one also, or maybe in the second column, there are entries that are not 0. And if so, then by doing row operations, you can put a 1 in the top column and use that one as a pivot to eliminate all the things underneath. So below the 1, there's only zeros. Then you go to the next one. And then there's two possibilities. Usually what's going to happen is that, or sometimes it's going to happen that you have something here that you cannot get rid of. Okay. So for example, once you put the 1 here, if you have a number here and you have zeros underneath, then you cannot get rid of that guy. That's a possibility. Or if you can get rid of it, then that's fine. But you continue, maybe you can't get rid of this one, but maybe here there are several entries here so that you can cancel this guy and make it a 0 by pivoting with some other guy, and then from the other guys you can put a 1 here and get zeros like this and so on. Okay. And again, it kind of looks like this. Maybe with these ones you're stuck with stars here, a star here. Maybe then in the next one you can do, you have a pivot, and then maybe star, 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 and then here you get 0, 0, 0, 1, 0, 0, 0, 0, 1. Okay. Row reduced echelon form. It looks like this. Okay. So why do I do this? Because I hope that this is starting to look like this to you. Because then I can take this guy and I can kind of compress, get rid of the columns that have zeros and ones and look only at the other columns. So let me compress this. By removing the columns that have zeros and ones and leaving only the columns that have stars. Okay. So what shape does this have? Well, I didn't, the rows are still the same. I still have k rows. How many columns did I remove? One thing that you need to remember from linear algebra is that if this is a full rank matrix, then there's exactly one pivot in each row. There's exactly k pivots, which means that I got rid of Actually, I'm sorry. I meant to only remove the columns of the pivots. I didn't mean to remove this one. So I just remove the columns with pivots. Okay. And so here, there's an empty column and there's two empty rows. So what did I do? I had n and I removed the k columns that have pivots so that now I have n minus k. Now, what are these stars? These stars are actually any element of the field. Okay. So you're free to put, in each star you're free to put any element of the field. Which means that how many ways are there of filling this guy with elements of the field? Or how many matrices are there of this form over SQ? The number of matrices. So I can fill this with, so fill the stars with elements from my field, my finite field. How many ways are there of doing that? Well, q to the however many stars I have. Q to the n, where there are n stars. Okay. So what did I just do? I started with a vector space. I chose a basis in whatever way, and then I simplified it with these row operations until I got it to a reduced echelon form, and I got to a matrix that looks like this. How many matrices are there of this form? Well, for each shape like this one, there's q to the m. How many shapes like this one are there? Well, this is exactly what we're summing over here, right? This is a partition. In this case, my partition is lambda equals 5. Again, so this is not English notation. This is in some other notation, but this gives me a partition 5, 3, 2. And this is a partition of 10 that has k parts. This has at most k parts, and the parts are at most of length n minus k. Okay, which is almost what I wanted. I want to have exactly k parts, which are less than or equal to n minus k. So why did I get almost that, but not exactly that? I think it's something that if I try to correct it in front of you guys, it's going to take me a while and I'm going to get confused. So in any case, this is meant to be a sketch of a proof. So in the forum, we'll see why it is that we got less than or equal here, where actually it should be exactly k parts. At least I think so. I wrote k parts here. Okay. But what's the point? The point is, again, you start with a vector space, you perform this procedure, and you get a matrix like this. And how many matrices are there? The number of matrices is you sum over all the different partitions of this type q to the number of stars of that partition. Okay. So given the vector spaces, I produced matrices like this. In order to complete the proof, what do I need to do? I need to prove that this was a bijection between vector spaces and matrices. Because I started with a vector space, and I produced a matrix like this. But I need to prove that this is a bijection. And this is just you need to kind of brush up on your linear algebra and think about it a little bit, and you'll see that this is a bijection. Okay. So this is a bijection. From the subspaces that we're counting to these tables that look like this. And this bijection gives the proof. Any questions about this proof? Again, I think you should take the time to remember exactly what this procedure of a reduced echelon form is. And I think we probably just missed some small detail about how row-reduced echelon forms work, which is what's giving us less than or equal to k parts instead of k. But a very small transformation of this proof is worse. Okay. So to step back a little bit, what we just did is that we were talking about these q-binomial coefficients, and we saw that to understand their coefficients are given in terms of these partitions, these nice partitions. And so this is one of the many motivations to learn about partitions. And so what I want to do for the rest of the hour is to go back to just talking about partitions. We're going to forget about this stuff and just talk about the combinatorics of partitions. So I said that P of n was going to be the number of partitions of n. And now let me define P sub less than or equal to k of n to be the number of partitions of n into parts less than or equal to k. Okay? So I just wrote that P of 5 is 7. And for example, what's P sub less than or equal to 3 or 5? Well, I need to look at these partitions and see which ones only use parts less than or equal to 3. So there's 5 of them. And these two don't count. And as usual, what we want to do next is try to understand these numbers. How do we compute them? Is there a recurrence relation, generating function, etc.? And so let me go ahead and show you the generating function for these numbers. So I'm going to fix k, okay? So you're only allowed to use parts 1, 2, 3, up to k. And we're going to consider how you can use those parts to form any number n, okay? And so what we're going to find is that the generating function for this is given by the product from I equals 1 to n of 1 over 1 minus x to the n. So here's the proof. Let's look at the right-hand side. This means right-hand side. This thing is 1 over 1 minus x, 1 over 1 minus x squared, 1 minus x cubed, 1 over 1 minus x cubed. up to 1 over 1 minus x to the k. All right? To the, oh, sorry. Here, k was fixed, and n is variable, and so this should be k right here. So this is for fixed k. So again, you're only allowed to use the parts 1, 2, 3 up to k, and you want to form any number n possible. So that's why I go up to k. Okay. Now let's take each one of these things and multiply it out. Or not multiply it out. Each one of these things is a geometric series. So let me take 1 over 1 minus x and write it as 1 plus x to the 1 plus x to the 2, which I'm going to write as 1 plus 1, plus x to the 3, which I'm going to write as 1 plus 1 plus 1, etc. Okay? Now, this one, 1 over 1 minus x squared is 1 plus x squared plus x to the 4th, which I'm going to write as 2 plus 2, plus x to the 6th, which I'm going to write as 2 plus 2 plus 2, etc. And so on. 1 plus x to the k plus x to the k plus k plus x to the k plus k plus k, etc. Okay. So then, now, okay, so we have this k power series. Imagine that you multiply all of them together. When you multiply all of this out, what's the coefficient of x to the n here? Well, to get an x to the n, you have to choose a term here, a term here, a term here, and so on. Okay? And so the ways of getting x to the n are the ways to write x to the n as x to the sum 1s, and then x to the sum 2s, etc., up to x to the some number of k's. Okay, you choose one term here, etc. But you see what it is exactly a way of writing n as a sum of 1s, 2s, 3s, up to k's. So this is, which is just what we want. Okay. Okay, so that's. I've always liked this proof a lot. The first time you see it, it's nice, it's simple, and it really explains why it is that that this gives rise to the partitions that we want. And now you can see that as we change the kinds of partitions, we're going to use very similar arguments to get their generating functions. So, for example, so this is for fixed k. Okay. What if now I don't have any fixed k, I just want to come from partitions? What should this be equal to? Well, just don't stop at k. And if you understand this proof, then for this one, the proof could almost just be the word clearly. It's the same argument, okay? Now, if you've never seen this before, I hope this expression makes you a little bit nervous. I don't know how often you've seen infinite products before. What does this infinite product mean? It seems clear that if this means something, it should be equal to this, but what does this mean? And if you're training this in analysis, then you can start worrying about, okay, does this ever converge, right? What does it mean for us, okay? So remember that we're not doing analysis here, we're doing computations in the ring of formal power series. So what do we mean when we say that we're gonna multiply, I mean, if I want to prove this, I would kind of write this, dot, 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 and then just put dot, dot, dot here, and put dot, dot, dot here. And erase this. Okay? That's a proof, but this is the step that should be a little bit worrisome, because we're taking infinitely many power series and multiplying. So how do I define the product of these infinitely many power series? Well, the way that we usually do this is that you're going to look at all the possible ways of multiplying a term from here, a term from here, a term from here, etc. But you should choose finitely many terms that are not 1. Okay? And the point is that if you don't do that, if you allow yourself to choose non-ones infinitely many times, then your exponent is not going to be an actual number. It's going to be infinite, right? If I allow myself to choose x to the 1 here, then x to the 2 here, then x to the 3 here, and I multiply things that all have positive exponents, that's an infinite sum of integers. That's not an integer. And so what we do is that in this infinite product, we force ourselves to take, okay, whatever you want, whatever you want, whatever you want, but there should be finitely many terms that are not 1. And this is the way that this is always done in algebra, and this is what we do here. So that's what this means. All right. So that's that. Okay, so we talked about partitions of n. We talked about partitions of n into parts less than or equal to something. Now, in the theorem that I raised earlier, we also had partitions into less than or equal to k parts. So why did I not define something like that here? So the reason is this. The number of partitions of n into at most k parts. Notice this is different. This is here the part should be less than or equal to k, and here there should be at most k parts. Different things. So for example, if n is equal to 5 and k is equal to, what did we do? 3. What are the partitions that count here? Well, you should have at most 3 parts, which means that this one is discarded, this one is discarded, and these one have at most 3 parts. So there's 5. It turns out that in general this equals the number of partitions of n into parts less than or equal to k. So it's like less than or equal to k and parts commute.
This comes from flipping the diagram or reading it sideways.
So there's different ways of proving it, but the simplest one, it comes from the Ferrers diagram. So there is an operation that you can do to Ferrers diagrams which is to flip them so that rows become columns and columns become rows. Okay, so this is going to be Now I put 5. 1, 2, 3, 4, 5. Then I have 4 in the next one. And then I have 1 in the next one. Okay. So lambda prime is going to be 3, 2, 2, 2, 1. Okay, and this is called conjugate. As is often the case for the word conjugate, it's nice if when you conjugate and then you conjugate again, you get back what you started with, and of course that happens here. And so what happens? Well, the thing is that lambda has less than or equal to k parts if and only if lambda prime has parts less than or equal to k. Right? Because lambda having less than or equal to k parts, the parts are the rows. So we're saying lambda has at most k rows. Now lambda prime having parts less than or equal to k, that means you have at most k columns. So what we're saying is that lambda has less than or equal to k rows if and only if lambda prime has less than or equal to k columns. That's pretty obvious. And so this is so in other words, conjugation is a bijection between these partitions and these partitions. So that's why yeah.
Even though they count the same thing, if you use the same notation to denote that, is it still p less than or sub less than or equal to k of n?
Yeah, because it's the same number, we might as well use the same notation.
Okay.
So this counts partitions with parts less than or equal to k or with less than or equal to k parts. Same number. Okay. Right. So let me prove a similar, a maybe more mysterious statement, which is that the number of partitions of n into distinct parts is equal to the number of partitions of n into, what do you think? It's kind of hard to guess, but into odd parts. These two sounded more similar to each other, and maybe it's not. It's surprising that they're equal, but I would say this is more surprising. So let's do it for 5. Which are the ones into odd parts? This one, and this one. 3. And which are the ones into distinct parts? This one, and this one. 3. So let's prove it. What should we do, algebra or combinatorics? Let's do both. I agree. So now you can imagine that combinatorics is going to require some cleverness, Because these things are kind of similar to, are different from each other, and somehow we need to biject from here to here. What about algebra? Does that sound easier? And by algebra, I mean generating functions. Well, one way of showing that two sequences are the same is showing that they have the same generating function. So, can we find, for example, the generating function for the bottom one? So the generating for element, let's call them A and B. This is going to be A. This is going to be B. Can we find this generating function? So sum from n equals 0 to infinity of, let's write P sub odd. What's this? What should I put?
Just the odd eyes.
It's kind of the same thing, except that I only put the odd term so that I only use odd parts. So I can use ones, I can use threes, I can use fives, etc. Okay. That's not too bad. Now what about the generating function for the first one, for A? So P distinct, let's say. What should I do?
1 plus x, 1 plus x squared, 1 plus x cubed.
So I can, so in order to ensure that I have distinct parts, I'm going to kind of write down the same thing, except that I'm going to make sure that I don't choose any repetition. So the first term was 1 plus x squared plus x cubed, but that meant repeating the number 1, and I don't want to repeat it. So I just write this. Okay, so either I don't choose the number 1 or I do choose it. And then either I don't choose the number 2 or I choose it. Either I don't choose the number 1 or the number 3 or I choose it. And in the end, in order to get an x to the n, you need to just choose some different x to the something which multiplied to x to the n. So that's going to be a partition into distinct parts. So you see, partitions are great in this way. I mean, it's fairly easy to write down their generating functions. What's not so great is that this is not clear at all why this should be equal to this. So how do we prove it? Well, this has 1 minus and this has 1 plus. How do we turn a 1 plus into a 1 minus? Use this trick that 1 plus x is equal to 1 minus x squared over 1 minus x. Right? What's 1 plus x squared? This is 1 minus x to the 4th over 1 minus x squared. 1 plus x cubed is 1 minus x to the 6th over 1 minus x cubed. Just difference of squares. So that's cool because I had 1 pluses and now I have 1 minuses, which is what I have here. So how do I get from here to here? Well, you see, the thing is that what do we get when we do all of this? We get the product. What do we get on top and what do we get on the bottom? On the bottom we get 1 minus x, 1 minus x squared, 1 minus x cubed. We get all the 1 minus x to the i's. This is overall I. And on top, what do we get? We get 1 minus x to the I only when I is even. Product over I even. Okay, so if I have all the evens here, and and I have all the i's here, then the evens cancel with the evens here, and I'm going to get 1 over the product over I odd of 1 minus 2. Yeah. Okay. Which is this. Any questions about it? So I hope you're beginning to be impressed by the power of generating functions, because we just proved this very beautiful combinatorial statement, and it seems we didn't do anything. We just kind of did, I mean, most of the stuff you could give it to your pre-calculus students and they can do it. But the machine is very powerful. I mean, not the infinite part, but anyway. Maybe some of your pre-calculus students could do a finite version of this. Now they could do it. If they cannot do it, you should really push them harder so that they can do a computation like this. It's finite version. The infinite version is too much for them. But, okay, so this is a generating function proof. Beautiful, beautifully simple, and we have absolutely no understanding of why this theorem is true. Right? It's one of these things where it's a proof but not an explanation. We still don't have any insight as to why this is true. We're certainly nowhere near. Well, actually, so what I'm going to do now is show you a bijective proof. And if you think about it in the right way, the bijective proof is motivated by this. So we're going to do, this was an algebraic proof. And now let's do a combinatorial proof. By giving a bijection. Okay? So given a partition into distinct parts. Okay? And I just chose one here. 4 plus 6 plus 12 plus 16 plus 20 plus 21 plus 32. And I hope I did this correctly. And this is a partition of 111. So here's a partition into distinct parts. And from it, I want to make a partition into odd parts. Okay? So, well, then we need to deal with the parts that are not odd, right? So how do you make something that is not odd, odd? How do you make 6 odd? Add 1, how else?
Oh, no.
Subtract 1.
Subtract 1, how else?
1 and 5.
I know it's an extremely big question, but how do you take an even number and make it odd? You could add 1, you could subtract 1.
Divide by 2. Take
You
the
could
one.
divide by 2, and then if it's not yet odd, then keep dividing it by 2. That's what we're gonna do.
Okay.
It works. The other one, it's another way, and I'm not aware of a way of making it work. I'm gonna take each one of these things and make it odd by dividing by 2 until it's odd. So split each part as power of 2 times an odd number. Okay? So 4 is 4 times 1. 6 is maybe. Okay, we're gonna do a 2-color proof now. So 4 times the odd number 1 plus 2 times the odd number 3 plus, then this one is 4 times the odd number 3. This is 16 times the odd number 1. 4 times the odd number 5. 21 is 1 times the odd number 21. And 32 is 32 times the odd number 1. Okay. It's something. Now, how do I turn this into a partition into only odd numbers? Well, what I'm going to do, group by odd numbers. Okay, so who got a 1? 4 plus 16 plus 32. Plus, who got a 3? Times 2 plus 4. Then, plus, who got a 5? 4. And then, who got a 21? 1. Okay? And I want a partition into only odd parts, and so I think the most natural thing to do, well, I'm allowed to repeat parts now. So what I'm going to do is then I'm going to write equals, just 1 plus 1 plus 1 plus 1 plus 1. How many times? 32 plus 4 plus 16 plus 32 equals 52 times. Plus, then 3 plus 3 plus 3, and then 5 plus 5 plus 5, and then 21 times, well, 21 is only going to appear once, right? So let's see, 3 appears 2 plus 4, which is 6 times. 5 appears 4 times. And 21 appears once. Okay? And so there you have it. That's a partition into odd parts. Okay. Why is this bijective? Well, in order to show this is a bijection, what we normally do is get the inverse. Okay, so if I started with this one, what would it look like? So, okay, so what does the inverse look like? The inverse looks like this. We have a partition of 111 as a big sum of odd numbers. And it happens to look like this in this case. And there are repetitions. 1 is repeated 52 times. 3 is repeated 6 times. 5 is repeated 4 times. And 21 is repeated once. So it's not repeated. Okay? What's the next step? How do I recover these numbers here? Well, you see, what I'm doing here is writing the number 52 in base 2. And there's a unique way of doing that. 32 plus 16 plus 4. So I write this in base 2. I write this in base 2. I write this in base 2. And I write this in base 2. Okay, so here, this step is base 2. And there's a unique way of doing that. Okay? And then what do I do? I take 32 times 1 plus 16 times 1 plus 4 times 1 plus 4 times 3 plus 2 times 3 plus 4 times 5 plus 1 times 21, which is 32 plus 16 plus 4 plus 12 plus 6 plus 20 plus 21. Now, why is this something into distinct parts? Because of two things. One thing is that when you write a number in binary, there's no repetitions. Right? Each power of 2 either appears or it doesn't appear, but it doesn't appear repeated. And so each power of 2 appears exactly once or 0 in this list, which means that these numbers that you're going to get here are all different from each other. Okay? And that means that these are different from each other. These are different from each other. This is different from itself. In each group, they're different from each other. And also, for each integer, there's a unique way of starting to divide by 2 until you get an odd number. And that's a unique odd number, which means that the numbers that appear here are different from the ones that appear here, the ones that appear here. And so the reason that this is a bijection is because of the uniqueness of writing a number in base 2. Which is a pretty cool reason, I think. But yeah, so then that's why this is a bijection, and this gives me a bijective proof of this fact. Now, again, I think maybe most of you have not seen this before, and it's a very clever bijection, and sometimes bijections take cleverness, but also in this case, you can take a hint from what happened here. Maybe I'll let you, because I'm out of time, maybe I won't try to explain how these two are related to each other, but I'll let you think about how it is that you might think of doing this from the algebra that took place here. Think about that. Do you have a question?
Yeah, I'm gonna be silly. I was just thinking about this because a bunch of us were talking about base 2 recently. It doesn't matter what our original number is written in. So our number is written in base 10. So it doesn't matter what base our number is written in. 2 is still a special base for this proof to go, right?
That's right. I mean, so it just happens that around here we prefer to write numbers in base 10. But what we need for this proof to work is base 2. And I mean, you can kind of see it partly because it's about odd numbers, and so that's it's about even or odd, and that's what the number 2 comes in there. But then within the proof, you can see some important details, like the fact that we don't have repetitions here. That's specific to base 2, right? So the statement that I made is not true for any other base. It's only true in base 2 that the summands here are different. But you could try to give a theorem for base 3. What does that look like? It's actually a very good question. Is there a base 3 or a base 10 version of this theorem?
So instead of bog, it'd be like 1, 1, 3 or something.
I'll let you think about it.